Topic 11, DC circuits. Part 2, Kirchhoff's laws. There are two Kirchhoff's laws. Kirchhoff's first law, which is the easier of the two laws to understand. It says the algebraic sum of all currents at a junction, like this one here, must equal 0. Or, put it in another way, the sum of the currents entering any junction in an electric circuit is equal to the sum of the currents leaving that junction. And this is based on the law of conservation of charge. Look at this one here. There are two currents entering the junction. There's one current leaving. And so, based on this law, the total current arriving at the junction must be equal to the total current leaving the junction. Now, let's have a look at a couple of examples. Example 1 here says calculate the value of current I, which is that one there. One of the currents leaving. You have one current arriving, 3 currents leaving. So we can write it this way. Currents entering equal to currents leaving. Current entering 3.6, this one here. And then currents leaving 1, 2, 3, add it together. And solve for I, 1.2 amps. Just simple algebra. This example is for you to solve and find out the answer yourself. You have to find out the current I, which is this one here. Here we go. Kirchhoff's second law, which is the harder of the two laws. In any closed loop in an electric circuit, the algebraic sum of the EMFs in the loop is equal to the algebraic sum of the potential differences in the loop. Don't forget, EMF is simply voltage produced by a power source. Potential difference is simply the voltage across a component, or the voltage used by a component. Or you could say sum of all EMFs equal to the sum of all potential differences around a circuit loop. And this is based on the law of conservation of energy, whereas the previous law, the first law, is based on the law of conservation of charge. Here is the example of a circuit that requires the application of both laws. And in this circuit, there are 3 unknowns: E2, I1, I3. E2 is this one here, unknown EMF. I1, this one. I3, this one. Here is the solution in detail. It says here, since there are 3 unknowns, we need 3 equations to solve them. So we had to come up with 3 equations. Right, it says, always apply Kirchhoff's first law for the start. Why? Because it is the simpler and easier of the two laws to apply to this. At junction B, which is that junction there, if you look at the previous slide, currents entering equal to currents leaving. There are 3 currents here. That one and that one is entering, and that one is leaving. So I1 plus I2 equal to I3. Now apply Kirchhoff's second law, and you have to consider a particular loop to do that. So consider loop ABEFA, which is that one there. ABEFA. And it says sum of EMFs equal to sum of potential differences. The voltage produced must be equal to the voltage used. There is a cell here somewhere with an EMF of 30 volts or 30 come on the side. And then as it goes through the loop, there's a resistor here with resistance of 20 ohms. So resistance times current gives you potential difference. And then you come to this other resistor here at the top, and its resistance is 50 ohms. 50 times I1, current here is I1. So there you are. Here's another equation. So 2 equations. we need a third one. So we need to consider another loop. It says here, consider loop B, C, D, E, F. This one here. And once again, you put down EMFs on this side, or the potential differences on the other side. But notice there are three minus signs, which mean that you are going against the conventional current as you go down the loop. So it says here, note, add negative sign if you go against the current through any component or battery. It is now for you to solve the three equations simultaneously by using your algebra skills. Have a go. Resistors in series. These three resistors are in series. It says here a number of resistors connected such that the same current passes through all of them. So same current passes through all of them. Deriving the series resistance formula. In other words, deriving the formula for resistance in series. Here we have a series circuit, a cell with an EMF, and two resistors, R1 and R2. It says here, taking the circuit loop we have, in other words, we're using the second law. So if we take a loop, let's say from here to all the way back to here. During our trip, we went through an EMF, which is that one there, so I'll put EMF on this side, on the left hand side. We also went through V1 and V2 on this side, because V1 and V2 are potential differences. Now E can be expressed as IR. R here is the total resistance. Current is common, because there can only be one current in a series circuit. V1, which is that one there, can be expressed as IR1, and V2 likewise can be expressed as IR2. And clearly I is a common factor which can be cancelled out, leaving us with R equal to R1 plus R2. And in general, we can extend it to as many resistors as there are in the circuit. Now we have resistors in parallel. A number of resistors are connected such that the total current is shared between all the resistors. So here we have three resistors in parallel, and then here we have the current coming along, and at this junction here the current is split three ways, and then these three currents rejoin to form the original current again. Here is the parallel circuit again, with three resistors in parallel, R1, R2, R3, and the currents flowing through them are I1, I2, I3. So initially the total current I coming along, and it splits three ways. And let's call this junction A, as is indicated here. Now let's apply Kirchhoff's first law to junction A. Currents entering equal to currents leaving. Current entering is just I. And then there are three currents leaving, I1, I2, R3. And the current can be expressed as voltage over resistance. So I is equal to V over R. I1 is equal to V over R1, and so on. Notice voltage is the same across each parallel branch, or each resistor is in parallel. So the common factor is V. V can be cancelled out, leaving us with 1 over R equal to 1 over R1 plus 1 over R2 plus 1 over R3. And in general, we can write it like this: 1 over R equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on.